Hello everyone, we are back again. Today we continue our journey with another supervised learning method. This time we will focus on one of the simplest supervised learning models called logistic regression. Last time we have discovered k-nearest neighbors. We saw how it works in theory and in practice. You can check that video with the link above. Let us start. We will start by introducing the method. It is a supervised learning algorithm. In its construction, it is suitable for binary classification problems where you have only two outcomes. It can be a task for finding whether a customer defaults or not, or a task that has outcomes of yes or no. In logistic regression, we model the probability of Y belonging to a category rather than modeling the response directly, which is the case in many regression problems. Now we move to the construction of the model. As you may guess, we are trying to build a model that shows the relationship between the probability of X and the dataset X. We use the notation of Px as the probability of Y equal to 1 given X. Since we are dealing with probabilities, our outcome should be between 0 and 1. So we must model Px using a function that has always a value between 0 and 1 for all values of x. We can use the logistic function, which is Px equal to e to the power beta 0 plus beta 1x divided by 1 plus e to the power beta 0 plus beta 1x. If you think about the logistic function, you will see that the function always stays in the range of 0 and 1. If you think about an example of defaulting, you can consider X as the balance on the customer's account. So in that case, the prediction of the model will be close to 0. However, it may never be below 0 because of its construction. The logistic function always creates an S-shaped curve of this form. Regardless of the value of X, we will obtain a sensible prediction. For fitting purposes, we will use the maximum likelihood method, which will be shown in the next slides. Recall the logistics function from the previous slide. What we will do is that we will manipulate a little bit and take the logarithm of both sides, where we end up the logistic regression model. That is, the logarithm of px divided by 1 minus px is equal to beta 0 plus beta 1x. As you can see on the slide, the logistic regression model is linear in X, which will help us with the interpretability of the model. We will use the maximum likelihood method for estimating beta 0 and beta 1. The basic intuition behind using the maximum likelihood method for fitting a logistic regression model is that we are looking for the estimates for beta 0 and beta 1 such that the predicted probability of having 1 for each data point corresponds as closely as possible to the data point's observed value. In other words, we are trying to find the beta values that represent the data well. The likelihood function is represented as L, and it is the product of probabilities where yi's are equal to 1 and 1 minus probabilities where yj's are equal to 0. As you can see, the likelihood function is parameterized by beta 0 and by beta 1. We are looking for the estimates of beta 0 hat and beta 1 hat, which maximize the likelihood function. Assume that you have established a model and you got the estimates of the coefficients. Your model estimated beta 0 as minus 8.5 and beta 1 as 0.006. Also, suppose that you have a test observation which has an x value of 1500. Then the probability of having 1 for that observation is almost 84%, which is quite high. However, if the value of x is 500, then the probability becomes less than 1%. So far, we have seen the real theory behind the logistic regression models. However, we will briefly talk about the extensions of the primitive model. The first extension would be the case where our data has more features than one feature, which will be the case for many real datasets. In that case, nothing really changes in our model except the additional terms for the logistics function. For that case, we have to sum over all beta coefficients and the variables x. For estimating the beta coefficients, nothing changes. We will again employ the maximum likelihood method for obtaining the best beta coefficients. Until now, our logistic regression models can only handle binary classification tasks. However, there are also tasks where you need to handle multiple classes. For those cases, we can extend the logistic regression model in multiple ways. Suppose that the response variable y has k different categories. The first way to deal with multiple classes is to construct k different models. Each model is supposed to classify one category from others. In this way, you can build k different models. For predicting a test observation, you need to get the probabilities from all k models, and you need to select the one with the highest probability. The second way to deal with multiple classes is to change the logistic function so that it incorporates all the k different categories. In this case, you can use the logistic function where in the denominator you sum over all k minus 1 categories available. Note that for multinomial logistic regression, you need to select a baseline scenario. Thus, you need to consider when you are interpreting your results. Today, we covered logistic regression, the theory, and the way of making predictions in practice. We also discussed its extensions, which are multiple logistic regression and multinomial logistic regression. We are looking forward to your feedback or questions. Thank you for watching our videos. You can ask questions by leaving a comment below, and we will do our best to answer it. In our next video, we will cover another fundamental algorithm in supervised learning, decision trees. See you in the next videos. Bye bye.